This is a video for AQA Further Pure Mathematics. This is Matrices section 2.5, in which we'll be looking at transformations in 3 dimensions. You're expected to be able to look at reflections in each of the planes, the XY plane, the XZ plane and the YZ plane. Now remember, when we're talking about 3 dimensions, we'd normally represent these by axes. The x-axis along to the from left to right, the y-axis going into the paper, and the z-axis going vertically upwards. So that's the way we would try and represent that on a piece of paper. So that the xy plane is all of those where z is equal to 0. If we're looking at rotations in 3 dimensions, then the positive sense of the rotation is to be anti-clockwise or counterclockwise when we're looking from the positive axis that it's rotating around. So for example, if we were looking at rotating about the z-axis, then imagine that you're looking down on this diagram up here, then our positive direction would be in this direction, rotating about the origin there. So the whole of the XY plane would rotate, or the whole of the space would rotate about that axis, so the Z-axis would be fixed. Now when it comes to calculating or finding the matrices for these, we do it in a similar way to 2 dimensions. But this time we have the points in 3 dimensions, or the unit vectors I, j and k. So I is a vector length 1, which is given by 1, 0, 0. J length 1 along the y-axis, so that's the vector 0, 1, 0, and k, the unit vector along the z-axis. So this is the vector 0, 0, 1. So put those together, and of course we make up the identity matrix for 3 dimensions. That's I, j and k. And if we look at what happens to those when we do a transformation, then that will give us the matrix. Or conversely, given a matrix, we can find out what it does by considering what has happened to those 3 vectors. So as an example of that, here's a matrix question. So that I dashed is given by the vector -1, 0, 0, j dashed by 0, 1, 0, and k dash by 0, 0, 1. So you can see here that j and k have not changed. So we would say that j and k are invariant. And what's happened is that I has transformed to negative I. So I goes to negative I, or in other words, I dashed is equal to negative I. Now if we look at that in terms of a diagram, what we're saying is that the plane which has got j and k in it stays the same. So this plane here is invariant, but I, which was over here, so that's j dashed and k dash staying in exactly the same place, I was here, comes across to this position, I dashed. So we can see then that this is reflection, where our invariant plane is this one here. So it's a reflection in the plane where we've got x equal to 0, or if you like, it's the YZ plane. Now, on the next slide, you'll see this in a nice sort of three-dimensional diagram. In our next example, we can see this time that both I and j have changed, but k dashed is equal to k, so k is invariant. Or in other words, the z-axis is invariant. And if we then mark that one in as being our invariant line, we can see that I dashed has ended up at this position here. This is I dashed, and j dashed is going back wrong in this direction, the negative y-axis, so this is j dashed. So I has turned through 180 degrees and j has turned through 180 degrees. So in other words, we've rotated the whole of the xy plane by 180 degrees. Remember that the positive direction, I mean, it doesn't, with 180 degrees obviously it doesn't matter whether it's positive or negative, but this is then a rotation by 180 degrees with the z-axis, so about the z-axis. We could say the z-axis invariant, or about the z-axis. And there again is a nice representation of that, and you can see that the whole figure has rotated. If you want to do some more investigation of transformations in 3 dimensions, then you can look at a Geogebra file, which you'll find at the following website. Well, that's the end of that video, and in the next one, section 2.6, we'll look at invariant lines and points.